Welcome to Semantic Web Technologies. This is Lecture 4, Knowledge Representations, Part 7, Resolution. First of all, we want to take a look at the resolution method for propositional logic, simply because it's easier. So, let us recall. Our purpose was somehow to build a machine for logic that is able to prove that a logical consequence is correct. So, for a formula f, can be said it is a logical consequence of a theory or a knowledge base T, only then if all models of T are also models of f, and you can write it in that way. So, then f is a consequence of T. But the problem is, if you want to build a machine to prove this, you have to consider all possible interpretations, and this, of course, takes a lot of time. So how should we do this in practice? By avoiding this. This is the same idea or the same intention that Gottfried Wilhelm Leibniz had when he proposed a mechanical method for solving logical problems. So, what we have to do simply is we have to come up with a syntactical method, not with a semantic method. And we have to implement the logical consequent simply by a syntactical method, which is also called a calculus. And for this logical calculus that we create, two things must be proven. First, the correctness, of course, that every syntactic entailment that is here written with this symbol, so every syntactic entailment also must be a semantic entailment. And of course, vice versa, you have to prove the completeness. All semantic entailments, on the same hand, must be syntactic entailments. And then you can use also the syntactic entailment method for the semantic entailment. So we do not make these proofs simply because we don't have the time and they are given in the basic mathematics lectures. So we want to apply a syntactical method, and its correctness, we assume that it has been proven before. But in this course here, I only want to teach you the method and not to prove that the method is correct. So the method we are considering is the so-called resolution, and it has been introduced by John Allen Robinson back in 1965. So what does it mean? So resolution is based on simple deduction rules and is a special form of enumeration, you can say. So instead of proving that a formula is a tautology, so it is true with any variable assignment, it deducts that a logical contradiction, or it deducts a logical contradiction from its negation. So, just take a look at this. So consider here we have a theory consisting of the formulas, clauses f1 to fn, and we say f sub 0 is a logical consequence of this theory. We can write this as is given here in the second line. So f sub 0 is entailed by this theory. Then we can go back to a logical statement which says that when I make or form a disjunction of all these, a conjunction of all these clauses, then it can be implied that also f sub 0 holds. And this is a tautology. So this is a simple equivalence transformation. When I negate this, then I have the negation of this formula. And of course, the negation of this formula must be a contradiction. When not negated, it is a tautology. And what we do then is we simply transform this into a clausal form. And on this clausal form, then, we will show that there really is a contradiction. Because resolution is able to show that there is a logical contradiction. And therefore, by proving that there is a logical contradiction inside that, we show that the first assumption holds, that this theory really entails f sub 0. So f sub 0 is a logical consequence of this knowledge base with f sub 1 to f sub n. So this is the basics of resolution. You are proving a tautology by deducing a logical contradiction from its negation. Okay, let's look at the basic step of the resolution. When you consider you have two clauses conjunctively connected, so you have a clausal form, and you have here in the first one the variables p sub 1 to p sub k, and here you have p, and then you have not q1 and all the negated variables on the other side, and here you have r1 to rm, and then you have s1 to sn, but both of these clauses contain the variable p, and the other contains not p, so not the negated form. And if this clausal form is true, then of course one of the both, either p or not p, must be wrong. Therefore, when I remove p and not p from these two clauses, then it must still be true, because otherwise it wouldn't be true with a 2. So this is the basic step. If you have in one of the clauses literal and in the other it's negation, then it holds you can remove this literal from the clause, because it holds that if you remove it, the clause that results from its removal also must be true. So, on the other hand, if you say that this one, the clause, without the literal p or not p, is a contradiction, then of course also the clause with p, and here not p, must also be a contradiction. Let's put it that way. You have here clause k1 and here clause k2, and you can transform this in a so-called resolution step to a clause k3. So you have here a knowledge base or a theory that contains clauses k1 and k2, and then you can entail from them the clause k3, where k3 doesn't contain the variable p, which is in both of the clauses on the one hand not negated, on the other hand negated. So the two clauses k1 and k2 can be transformed into a new one, k3. And what you do is you proceed with all your clauses by removing the same literals that are in one clause negated, the other not negated, and somewhen, maybe, you will come to an end that clauses are resolved that consist only of an atom and the negated atom, and then you will receive the so-called empty clause. So here this bottom element, this is the empty clause, and then you have shown that there is a contradiction. So that's the basic step of the resolution. So in general, how to deduce a contradiction from a set of clauses is done in the following way. Let's consider we have a set M of clauses. What we do then is we select two clauses from M and try to create a new clause via a resolution step. If the new clause already is then the empty clause, then a contradiction has been found. And if not, the new clause K is added to the set, and we continue here with step 1 and select another two clauses. This procedure has been shown for propositional logic to be correct and also to be complete. So, now how do we prove that a formula psi is a logical consequence of a knowledge base or a theory phi of clauses, so that psi can be entailed by phi? Just simple. We compute the negation of the implication that phi implies psi, which is a contradiction. So we have here not phi implies psi, and this is equivalent to phi and not psi. What we do next is we determine the clausal form of this formula, and then we select simply two clauses from this formula and try to create a new clause within a resolution step. If the newly created clause is the empty clause, then a contradiction has been found, and we are done, because then it holds that the original formula we had here really holds or is true. So phi entails psi. On the other hand, if our formula that is the result of the resolution step is not the empty clause, then we add this formula to our knowledge base or to our theory, and we continue with step 3. Let's do this with an example. So here we have a simple example in propositional logic. You see we have here a knowledge base phi of 3 different facts. We have here, first fact, if it rains, Jane brings her umbrella. So we represent if it rains with R, and Jane brings her umbrella with U, and then we have R implies U. The second fact would be if Jane has an umbrella, she doesn't get wet. So Jane with an umbrella, again, is U, and doesn't get wet means not W. And the third fact is if it doesn't rain, so not R, then Jane doesn't get wet, so implies not W. So now we want to prove that Jane doesn't get wet. So the statement that we want to entail from this knowledge base is not W. So what we have to do first is, of course, we have to look at the negated form of the thing we want to deduce. It means not W, negated is double negated W and is W, and we add this W to our knowledge base. And you see here we represent the knowledge base simply as clauses. So in the first clause, you have not R and U, so the transformation here has been made. As you see here, implication is substituted by disjunction. And then we have the second clause here, not U, not W. You see here U implies not W is substituted via this transformation to this clause. And also the third clause then is translated into R, not W. And the negated thing that we want to entail, the negated fact that we want to entail, is also added to the knowledge base. So this is the new knowledge base. It's phi and not psi. It's the negation of the thing we want to entail. And here, now, with the help of the resolution, we want to find a contradiction. So let's start. We select simply 2 clauses from the knowledge base. We select clause number 3 and clause number 4. And here we see we have W and not W in these 2 clauses. Therefore, W and not W can be removed, and the result will be R. And R will be put into our knowledge base as clause number 5. Then we select again 2 clauses. So let's take 2 and 4. Then we have not U and W as number 2, and we have W as number 4. So you see again, W and not W, negated, not negated, the same variable, they can be removed, and the result of this resolution step is not U. And we add not U to our knowledge base. Then we take another 2 clauses from our knowledge base. Let's take 1 and 5. Then we have here not R, U, and R, which was number 5. And you see here R and not R, they can be removed in the resolution step, and the result will be U. And we put U into the knowledge base. And here we already see we have here number 6 and number 7. These are only 2 atoms or 2 literals that are negated and not negated. And the resolution step from 6 and 7 computes to the empty clause. So the result is the empty clause, and therefore we have found a contradiction in the knowledge base. And therefore, vice versa, it holds that our original assumption holds, that psi can be entailed from phi. So Jane doesn't get wet. While for propositional logic, this is pretty simple. For first-order logic, the resolution is a little bit more complicated, because we also have to take into account, as you see here, the transformation of quantifiers and stuff like that into a clausal form. And then again, we also have to take into consideration that we have real variables. We don't have real variables in propositional logic. And therefore, we have to make some substitutions and unifications. But we will learn this in the next part of the lecture.